Hello, I'm Vincent, an undergrad at MIT, and my teammates Franklin and Eric are undergrads at Harvard. Today we'll be talking about our implementation of pressure field models. So before we get into pressure field models, you might ask, what's wrong with just having rigid body physics models? And there's a number of reasons we don't like rigid body physics. For example, even having very simple simulations requires a lot of attention to detail. We saw in class that if you just want to simulate a scenario where there's a ball that falls onto the ground, you have to choose damping coefficients and other details very carefully to get the ball to stay there. And another reason is that real-world contact between objects is non-rigid and occurs over surfaces. For example, when you grab a ball, your hand and the ball are both deforming and they intersect at an entire surface where the force between the objects is being applied. So now what are pressure field models? Basically, we'll model each object as a bunch of tetrahedra with a pressure function. The pressure function will be 0 at the object surface, and it'll be larger in the object's interior. And basically, you can think of this as, for example, when you poke a rubber ball, the further in you try to poke, the more resistance you'll encounter, and that's what we mean by pressure. And now when two objects come into contact, we compute the intersection surface where the two pressure functions are equal, and we integrate pressure over that surface to get the force between the objects. And for an example of what this looks like, here are two objects that are intersecting, the red one and the blue one, and the equipressure surface where the two pressure functions are equal is shown in green. And now if we integrate the pressure function over that entire green surface, we get this green arrow, which is the force between the two objects.
Now we're going to talk about the tetrahedron intersection problem and our optimizations to make it run faster. The main computation in this problem is looking at all pairs of tetrahedra and then finding the equipotential surfaces to integrate over. The most expensive operation is finding the intersection of two tetrahedra and a plane, which is done by expressing a tetrahedron as an intersection of four half spaces. Since this is the slowest part of the code, we tried very hard to speed it up, but it's very, very hard to do without compromising accuracy. As you can imagine, this problem has a lot of corner cases in it. Sometimes the best way to do something quickly is to do it less often. Inspired by this, can we find only the pairs of tetrahedra which intersect? Because those are the only pairs of tetrahedra that actually matter. A common way to speed up searches is by building an index. Here we use an R star tree. And when you build an index for every tetrahedron in A with a pose of AT. You call this index DT, and then you search the index DT for every tetrahedron in B transformed by the pose of B. And you do this for t equals 1, t equals 2, all the way to big T. However, this requires building an index big T times. Can we do better? We can also let D1 be the index built with the identity pose in A. Note we only build the index once, and then simply search this index for the pose of A inverse times the pose of B on each tetrahedron in B. Along with generalized bounding boxes, this yields a 13 times speedup.
Thanks, Franklin. I'd like to talk about the third part of our project now, which is Civic Simulation. So this asks the question, we have this really great algorithm for computing forces between objects. How do we go from the forces to the movements? So the way we model this inside our code is that each object has a fixed geometry, which doesn't change over time. This is the actual tetrahedral mesh. But we also provide the object with a time-varying six-dimensional pose, which is a translation and a rotation, both three-dimensional. So equations of motion for rigid bodies are the angular acceleration is proportional to the torque, and the linear acceleration is proportional to the force. We update the velocity and angular velocity over time through a simple Euler method, and then we update the poses by applying an exponential map on the special Euclidean group in 3 dimensions. The reason why we update the velocities first is for stability reasons due to a semi-implicit Euler integration. Furthermore, because contact forces by themselves aren't that interesting, we also allow the user to provide a callback that allows them to add other forces like gravity and making some objects static to make the visualization more interesting. So let me show you a demo right now. So this is an interactive Julia notebook. So here's an example of how our simulation works. We define a world with 3 objects, a sphere, which is a translated icosphere, the ground, which is a cube that's also translated, and a ramp, which is a cube that's rotated and translated. Then we run the simulate function, which returns a list of poses for each object over time at each time step. And by changing the time step, you can see the pose for the translation of the rotations of the objects moved according to gravity and contact forces. So that's all we had for this project. Thanks so much for listening.